Let's wrap up our discussion on photonic crystals with a few concluding remarks. So first of all, quick recap. Photonic crystals, they're periodic structures that are designed in such a way that they have a band gap, meaning that for a certain frequency range, there's no propagating modes of light that can go through it. So if you excite that structure within that frequency range, the light has no choice but to get reflected. So it's basically a fancy mirror, if you want. But what I actually want to do here is make a comparison between the photonic crystals on one hand, and then the more traditional electronic crystals, regular crystals, as you know them from semiconductor solid state physics. So if I make a table like this with the photonic version in the second column and the electronic version in the first column, then we can contrast these two structures and see what similarities and what differences there are. First of all, yeah, it's no big surprise that the electronic crystals, they use electrons as particles running through it. And here on the right-hand side, we have photons, of course. Okay, that's rather trivial. But what's more interesting to look at is what is the thing that varies periodically. For our photonic crystals, we know that we have a change in refractive index that causes the scattering and then all the interference. For the electronic case, the thing that varies periodically is just the electron potential that you have in a crystal. So that also causes the scattering, the interference, and then that gives rise to a band gap. What we can also say is that the equations that govern the behavior of these two cases is different. For the electronic case, we have the Schrödinger equation. And we have, of course, our friend Maxwell in the photonic case. But what's more relevant and more interesting is that the Schrödinger equation is a very easy scalar equation, whereas for Maxwell here, we have, of course, the vectorial nature of light. So this is, of course, important because we've seen, for example, for photonic crystals, that you might have the situation where you have a band gap in one polarization but not in the other polarization. So that's a complication that's not present in semiconductor physics because of the difference between scalar and vectorial. So band gap opens, and then we have the bands here, which are called the valence band and the conduction band in the electronics case. And we speak about dielectric bands and air bands in the photonic case. Okay, that's just a piece of terminology. Another interesting difference is the length scales involved. So for the electronic crystals, we're basically talking about stuff happening with a periodicity on the order of an angstrom, whereas for our photonic crystals, we have stuff happening on the order of the wavelength of the light. So in a material that's basically then hundreds of nanometers. So the length scales are completely different. And then a final interesting difference is that, yeah, the electronic crystals, you can basically just find them in nature. They're not really fabricated atom by atom. So you can say that these are naturally occurring. Of course, you need to help nature from time to time to make a very pure crystal and things like that. But it's not that you assemble these things step by step in a bottom-up fashion. But photonic crystals, on the other hand, they are mostly man-made. So you can make them with lithography, where you drill some holes in a piece of semiconductor and then make your photonic crystals that way. There are some exceptions. I mean, there are photonic crystals that naturally occur in nature. For example, wings of butterflies and things like that. But most of the time, especially in the applications that we're looking at, we're dealing with man-made structures. Because, yeah, that's a nice segue to talk indeed about the applications. Just like in the electronic case, things only start to get interesting when you introduce defects into the crystal. The same thing is true for these photonic crystals, these photonic structures. So if you have structures like these where you've introduced defects, for example, a point defect, a line defect, or a surface defect like this, then you can do all sorts of interesting things. So pause the video and see if you can think about what the role, what the purpose of these three different structures could be. So remember, if we're in the band gap, the photonic crystal acts as a perfect mirror. And this is indeed what's happening here in this right-hand figure. where you have made some sort of fancy mirror with holes in. If you're in the bandgap, then you get 100% reflection over here. Okay, that's perhaps not so spectacular, but more interesting is, for example, this case over here, where you have a line defect. So now you just have a region of space which is bounded on two sides, the top and the bottom here, by this perfect reflector. So in this case, the light has no choice but just to propagate along this line here. So you've created a waveguide in this particular case. And then finally, over here, this point effect, you have a region that's surrounded on all sides by this perfectly reflecting mirror. So in this way, you have a cavity that you have created, which can be used as a filter, for example. And the nice thing about these mirrors, especially if you compare them, for example, to regular metallic-based mirrors, is that they can be made much lower loss, because mirrors based on metals always have some sort of absorption loss. But here, it's based on a different principle, purely dielectric media, and then reflections and interference. So in this case, you can get reflectivity up to 99.99%, provided you have enough periods over here. So these are just some examples of how you can use these structures to, for example, miniaturize the behavior of light here on a chip. If you have a chip with a photonic crystal here, and then you can guide it along a band or split it or couple it to a resonator and things like that. So these are some ways you can use these photonic crystals on chip. Another possible application is specifically design these structures, these periodic structures, to engineer a very specific dispersion profile, which could be useful for all sorts of nonlinear applications, for example.